Good morning everyone, my name is Abdul Qadir Mahmoud and I will present to you my paper which is about two output spin wave programmable logic gate. To start with, I will give you a brief introduction about the spin wave based technology, then I will explain to you the proposed structure of programmable logic gate. After that I will discuss the simulation results and performance comparison with you, and in the conclusion I will sum up. Processing the enormous amount of raw data resulted due to the past decades' information technology revolution requires efficient computation platforms. CMOS downscaling has been sufficient to keep improving processing performance to match these requirements. However, CMOS downscaling become more and more difficult due to various technological hurdles: leakage wall, reliability wall, and cost wall. Therefore, new technologies have been explored to find an alternative for CMOS. One of them is spinwave. Spinwave-based technology stands apart as a promising alternative avenues because its wavelength can reach down to nanometer, its device can operate up to terahertz range, it has an ultra low power consumption because it doesn't need the charge movement, it has an acceptable delay in addition to the intrinsic data parallelism. Different logic gate has been proposed in the literature. However, this magnetic technology provide only one output which cannot provide fan-out capability. Therefore, if the output of such a gate should be fed to multiple following gates inputs, it must be multiple times replicated, which result in a substantial area and energy overheads. The problem of fan-out is solved in this paper, and multi-input, multi-output programmable logic gate structure is proposed. The contribution of this paper can be summarized as follows. Design of two input, two output programmable logic gate, two logic functions including AND, NAND, OR, NOR, XOR, and XNOR can be implemented using a single two-output structure. For example, the gate AND and XOR can be implemented at the same time for the same inputs. The second contribution is the validation of the gate functionality using the object-oriented micromagnetic framework software. And finally, demonstration of the superiority. The evaluations indicate that the proposed two-output gate saves 33% of energy and 16% of area without incurring any delay penalty when compared with the functionality equivalent design based on state-of-the-art spin wave gates. In addition, the proposed design outperforms 15 nanometer CMOS in terms of energy and area by providing an energy reduction of 42% while consuming 12 times less area. In a magnetic material, the magnetization can be exploited for memory or computation purposes. For example, in a magnetic equilibrium state, the magnetization is static, which can be utilized to design a spintronic memory device. When the magnetization is out of equilibrium, it is subjected to a dynamical motion due to its magnetic torque. The mathematical description of this magnetization dynamic is given by this equation, which is the Landau-Lifshitz equation. For small magnetization interruption, the equation can be linearized and has wave-like solutions. These wave-like solutions are called spin waves and can be seen as a collective excitation of the magnetization. Just like other waves, the spin wave has a wavelength and wave number. The wavelength, which is the distance between two consecutive electrons which exhibit the same spinning behavior. Now we saw the spin wave. How can we benefit from the spin wave? Waves interaction is based on the wave interference principle, such that if two spin waves meet at a crossing point, then if they have the same phase, then they will constructively interfere with each other, resulting in a bigger wave. Whereas if they are out of phase, then they will cancel each other because they destructively interfere together. Now moving to the proposed programmable logic gate, which has a ladder shape structure. It has two data input and two control inputs and two outputs. Now in order to design to obtain the proper functionality at the outputs, the programmable logic gate structure must be designed carefully such that the dimension reflect the functionality of the gate. For example, if the required interference patterns is that to interfere constructively if the spin waves are in phase and destructively interfere if the spin waves are out of phase, then d1 to d5 should be equal to n times lambda, where n equal 1, 2, 3, 4, and an integer number. Additionally, the place of the output is an important factor to detect the output. In contrast to CMOS, inverted and non-inverted output can be generated without adding any extra element and just by shifting the place of the output detection, such that if the non-inverted output is desired, then D6 and D7 should be placed at a distance of n lambda of the last interfering point. Whereas if the inverted output is desired, then it should be n over lambda, n over 2 multiplied by lambda from the last interfering point. To explain the operation principle, we will take the left arm as an example. The spin wave will be excited at all input at the same time with the same amplitude and frequency, and they will propagate in both directions horizontally and vertically from the control. Now moving to the left arm, the spin wave excited at C1 and the spin wave excited at I1 will interfere constructively or destructively depending on their phase at this point, and then the result will propagate downward to interfere constructively with the spin wave excited constructively or destructively with the spin wave excited at I1, and the result of interference will propagate downward to be captured at the output. Now we have two main methods to the output: detection based on the phase and detection based on the threshold. The detection based on the phase is based on a predefined phase reading, such that if the spin wave has a phase of pi, the result is logic 1, whereas if the spin wave has a phase of 0, then the result is logic 0. On the other hand, the threshold detection method is based on a predefined threshold, such that if the output magnetization is greater than or equal to a certain threshold, then the gate output is 0, whereas the output is 1 otherwise. Different functions can be obtained at the output based on the output detection method and the control inputs. Now taking the output detection by spin wave phase at the beginning and C1 equal to 0 and C2 equal to 0, then O1 and O2 will be the result of AND gate of I1 and I2. Whereas if one of them is 0 and the other is 1, then this one will be AND of I1 and I2, and this one will be OR of I1 and I2, and likewise the third and fourth case. Whereas if the output detection is based on the threshold, then the control input is not important, and regardless of it, XOR or XNOR will be captured of the I1 and I2 will be captured at O1 and O2 based on the determined condition. Moving to the design parameters, which should be passed to the micromagnetic simulation. Now we use the perpendicular magnetic anisotropy, which has saturation coffee B, which has the saturation magnetization 1.1 mega ampere per meter, and the rest of the parameters. And here are the dimensions, which equal to 110 nanometer, which equal to the wavelength. Moving to the simulation results of the AND OR gate simulation result. Here is the simulation of the case where the control input here is 0 and here is 1. Therefore, we will obtain at O1 AND of I1 and I2. O2 will be OR I1 and I2. Whereas O2 will be NOR and O1 will be NAND gate. Red, the color code is that red present logic 1 and blue present logic 0. Let's examine two cases. For example, the first two cases, 0, 0, 0, then the output should be 0, as the AND of 0 and 0 is 0, whereas the NAND is 1. In addition, moving to the OR gate, 0 or 0, it will be 0 again, whereas the NOR, it will be 1. Moving to the second case, 0 and 1 will be 0, 0 or 1 will be 1, 1 or 0 will be 0 again, 1 or 0 will be 1, 1 and 1 will be 1, 1 or 1 will be 1, which prove the correct functionality of the proposed AND OR gate. Moving to the XOR gate, now we analyze when control 1 equal control 2 equal to 0, and for different cases. Now the predefined threshold is 0.41, which is the average of the two cases which are at the edges. Now the condition is that to implement XNOR, it will be if the magnetization angle greater than 0.41, it will be 1, which means that 0, 0 and 1, 1 is equal to 1, 1. And if the magnetization angle is less than 0.41, then the output will be 0. This means this is 0, which means the XNOR gate. Whereas if I want an XOR gate, then the condition will be flipped, such that if the magnetization angle is greater than 0.41, then the output will be 0, 0, 0. Whereas if the magnetization angle is less than 0.41, then both of these will be 1. Now, in order to compare and assess our structure, we instantiate the 3 input majority gate to compare it with the other majority gate in the state of the art. Now, and we validated it using micromagnetic simulations. Now, as you can see here, 0, 0, 0, the output is 0, 0, 0, 0, 0, the output is 0, and the same cases for all of them. 0, 1, 1 will be 1, 0, 1, 1 will be 1, and the same line of reasoning can be implemented on the other cases. Now the performance comparison with CMOS and state-of-the-art spin wave, our evaluation indicates that while 14 times slower than the CMOS counterpart, the proposed gate provides a 42% energy consumption reduction while requiring a 12 times smaller area, as you can see. On the other hand, when comparing with the state-of-the-art spin wave majority gate, the proposed structure saves 33% energy and 16% area while keeping the same delay. In conclusion, we introduced and evaluated by means of object-oriented micromagnetic framework simulations a novel 2-input 2-output spin wave based programmable logic gate with a ladder-shaped structure capable of to evaluate any pair of AND, NAND, or NOR, XOR, and XNOR Boolean functions. To get insight into potential practical implications of our proposal, we made use of such a gate to instantiate a 3-input majority gate, which we evaluated and compared with the state-of-the-art equivalent implementations in terms of area, delay, and energy consumption. Our estimates indicated that the proposed gate provides 33% and 16% energy and area reductions, respectively, when compared with the spin wave counterpart, whereas 42% energy reduction while consuming 12 times less area when compared to a 15 nanometer CMOS implementation. That brings me to the end of my presentation. Listening, and you are welcome to contact me at any time for the questions. Thank you.